Hello everyone, I'm WeiWei. I am 2080 Beckman Young Investigator. Today I'm going to talk about how to use the chemistry perspectives to design high TC superconductors. So first of all, what is superconductor and what are the applications of the superconductor? The first very interesting properties of superconductor is the expulsion of the magnetic field. Here, this is a ferromagnet, and this is a superconducting material. If we cool superconductor below the critical temperature, and the ferromagnet will be lifted up, and this phenomenon is called Mansell effect. If we use the superconducting material to make the magnetic levitation train, there will be no contact between the train and the rear. And another unique property is a zero electrical resistivity. Similarly, if we cool superconductor below its critical temperature, the resistance will be gone. And if we can use the superconducting material to transfer electricity, we can get zero power loss. And another very unique property is the Josephson effect. And that's to say, for the superconductor, a current can flow infinitely long without any voltage applied. And we can use kind of mechanism to make the new devices. And this kind of devices contains two or more superconductors and coupled by a weak link, such as insulator. So here you can see this is superconductor A, superconductor B, and they are separated by an insulator. And for this kind of device, and the current can go through from the superconducting A to superconducting B, and will not be stopped by the insulator. And this kind of device is very important and critical for the quantum qubits in the quantum computing. And superconductor is so interesting and so important. However, there are a lot of challenges in this field. The first superconductivity was observed in Mercury in 1911. After almost a half century, the first superconductivity theory was proposed, and that's the famous BCS theory. And after another 30 years, the first high TC superconducting family was discovered, and that's the famous cuprates. And after another 20 years, the second high TC superconductor was discovered in the iron arsenic. So based on the experiment passed in the 100 years, and we can tell superconductor, it's almost impossible to predict the superconductivity. And the theory is behind the experiment a lot. And the most important thing is we need to explore more new systems to host the high TC superconductors. So I was funded by Beckman Young Investigator program since 2018. During the past 2 years, there are 9 new superconductors. There are 8 new superconductors was discovered in my group. The highest TC so far we made is 9 Kelvin. And today, well, I cannot talk all the superconductors. Today, I just want to talk about a very interesting one. That's a new magnetic superconductor, Yb PT5 phosphor. And I will explain how we come up with the idea and how we characterize it and how we interpret it. So first of all, as we know, it's very, very hard to make the magnetic superconductor because magnetism will kill the superconductivity. However, we want to make that one because it's very important to understand the interplay between magnetism and superconductivity, because the mother compound of the two high TC superconductors, they're all magnetism. And people try to kill the magnetism and generate the superconductivity. So that's why it's very important. It's hard, it's very challenging, but it's very important. So how can we come up with this idea? How can we try to design this kind of new material? First of all, we have a targeted property in material. So our goal is make the magnetic superconductor. That's to say this kind of material should have magnetism and a superconductivity. And then we try to translate this kind of concept of physics in magnetism and superconductivity into a chemical requirements for synthesis, and using like the structure, electron counting, chemical bonding, these rules. And then we will use inorganic synthesis to make this kind of new material. After we made the new material, we will do some theoretical calculation and to interpret their property as well as modify the chemical requirement for the synthesis. So there is a very famous material that's called heavy fermion superconductors. For example, cerium cobalt indium 5. And for the cerium cobalt indium 5, and cerium shows the magnetism, and the whole compound is a superconductor. And we can consider this kind of superconductor as a combination of the magnetism and the superconductivity. So this is the crystal structure of the cerium, cobalt, indium. And then our idea is, can we come up with some system that can be like an anti-cerium, cobalt, indium? Okay, so now we have the structure idea. So the second one is what kind of chemical elements we will pick up. So what we did is we pick up the Pt and phosphor. So how can we come up with this idea? Our idea actually is coming from this iron arsenic superconductor. This is the barium iron arsenic superconductor. If we dope the potassium into the system, the Tc can go as high as 35 Kelvin. And this new superconductor was discovered in 2008. However, this superconductor can be traced back to 1994. That's the yttrium nickel to boron to carbon superconductor. And let's see how similar these two compounds is. Okay, so here, this is the barium, yttrium. Of course, both of them crystallize in the same space group. And barium, yttrium, and the transition metal iron, transition metal nickel. And here is arsenic. Here we have a boron, carbon, boron. This is single chemical unit. And then this nickel, boron, carbon, boron, total electrons is 15. So what we try to do is let's replace the nickel, use Pt, because Pt is very easy to be spin polarized. And then we also replace phosphor. We also use the phosphor to replace the, okay. We also use the phosphor to replace the boron carbon 0.5, and we get the same electron counts. So our goal is now we try to synthesize the new superconductors with Pt phosphor pair in the anti-cerium cobalt indium 5 structure type. So then we're starting from the rare earths. Okay, we did all the rare earths experiment. Here we just talk about Yb. And then usually what we do is we put a Yb and PT5 phosphor and Yb with different ratios from the 20% to 100%. And what we find out, okay, Yb can have, we can make the solid solution. Yb, the low ratio can be as low as 20%. The high ratio is fully occupied. So this is the crystal of the Yb, crystal structure of the Yb PT5 phosphor. And we can see Yb go to the cerium side, rare earth side. And then phosphor, this is the main group elements, go to the cobalt side. Okay, however, the transition metal, Pt, go to the indium side, so they're opposite. So that's exactly the anti-structure of the cerium, cobalt, indium 5. And this is the Pauli pattern of our compounds. And we can see, usually we always have some unreacted Pt, very small, and a very small Pt phosphor to binary phase. Okay, so what we did is, first of all, we want to study the magnetic properties of the Yb X PT5 phosphor. And we measure the magnetization changes with temperature and with field. And by feeding the data, we can get Yb is 3+. Okay, so that's a Yb 3+, not Yb 2+. And moreover, we measure the heat capacity below the 1 Kelvin. So we measure the heat capacity as low as 0.1 Kelvin. And then we can see here, this point, this is a 0.3 Kelvin. And we see an antiferromagnetic transition of the Yb3+ at 0.3 Kelvin, very, very low temperature. And then we calculate the entropy change, this corresponding to the spin 1/2. Okay, so now we see this is magnetic. How about the superconductivity? So we measure the resistance. And for the, what we find out is for the low ratio Yb sample, for example, Yb 0.25, Yb 0.29, and we see a completely superconducting transition around 0.6 Kelvin. Okay, however, we didn't see this one in the high ratio Yb. That's to say, as we increase the Yb, the superconductivity was killed by the magnetism. However, at a low ratio Yb, we still see the superconductivity, which is very lucky, okay? And then we try to understand what's really going on behind it. So what we did is we calculated the electronic structure of the Yb PT5 phosphor. And by applying spin optical coupling on the Yb and Pt, and we figure out no matter which kind of method we are using. So Yb3+ is always show the magnetism. So Yb3+ job is play the magnetic role. However, the Fermi level usually are dominated by the hybridization between the Pt and phosphor. And this one gives rise to the superconductivity in this YbPt5 phosphor compound. So now the picture is clear. So Yb, rare earth, in charge of magnetism. And then that superconductor is coming from the Pt phosphor. And as we increase the Yb ratio, go to a very high ratio, and this magnetism will be very strong and kill the superconductivity. So this is our story about YbPt5 phosphor. Okay, so this is our story. And in the end, I would like to thank Beckman Young Investigator program. And this program is giving me all the freedom, do whatever I would like to do. And I have a lot of ideas, so I just try it. And then I really appreciate my graduate student, Xingui. Now he already graduated. And all this beautiful work is done by him. And also my student, Runway, and now she's continuing to working on the superconducting project. And my collaborators at Poland and Oak Ridge, Georgia Tech, and MagLab, and Peking University, Arizona, they are very helpful to help me to measure the temperature down to 0.1 Kelvin. And that's very important for the research. And in the end, thank you very much.